Good Lord, ride all the way.
A 10,
9,
8,
7,
6,
5,
4,
3,
2.
1.
Hey there, everybody, and welcome to Slooh. My name is Eric Edelman, and today we are looking at the sun. There it is. This is the sun from our partner, Matt Francis, in the Prescott Observatory. A beautiful, beautiful image of our sun. This sun really does hog the spotlight, sort of the crown jewel of our solar system, if it were. And this sun, it's always changing, always evolving. This change makes it endlessly interesting to observe all the time because there's always new things that are going on. It's gorgeous to look at if you have the right equipment. Please, anybody who's watching this, do not go out and look there for yourself unless you have that proper equipment. You will regret it. And also, this sun, what effects it has, what changes that are occurring on this sun, they can be a little bit hazardous to modern life here on Earth. So those changes and those potential hazards that they do bring, that's why we are here today. Earlier last week, during our regular solar viewing hours here at Slooh, we did notice a dark spot on the edge of the sun. And some further investigation did tell us that the spot was a massive area of solar activity. So we put together this show to investigate it further as it slowly makes its way across the solar face. And really, you can tell that these images are pretty live because we actually are seeing clouds coming in front of our view of the sun here. It's actually monsoon season over in Prescott, Arizona. So it's lucky that we actually get to see the sun as it is. And we see it right now as a very dynamic image and also belying the whole sort of truth of it being a very dynamic sun. So what are we looking at here? Well, we'll get into the specifics of these images a little bit later with our guest Bob Berman, but this here, it is the sun right now. And they're coming to you directly from from our partner, Matt Francis at Prescott in Arizona. And so even if you could look directly at the sun without frying your eyes, you wouldn't be able to see the kind of detail here that we're seeing with our screens right now. This telescope is bringing you the sun in HD. So during the broadcast today, we're actually going to be looking up close and personal at this sun, exploring the different active regions and talking about the different kinds of solar activity, including things like solar wind and massive solar flares. Actually, according to reports, a co-rotating interaction region, a CIR, that came from the sun is actually expected to reach Earth today. Nothing that's going to be any way really hazardous or anything like that, but we'll talk a little bit more about what that means as the show goes on. We'll also be discussing the kinds of damage that solar activity can do to modern technology, knocking out cell phone networks, causing navigational problems, and even causing blackouts. And speaking of blackouts, yes, we appreciate you joining us here today, even though this show was initially scheduled for Monday, but had to be postponed due to a blackout at the studio. So power outages can actually be pretty devastating, but not to worry. This one was more due to overuse of air conditioners than the sun itself, so more of a secondary effect of that sunlight, if you will. So no, the sun did not silence us as we started to attempt to record its dark side. No conspiracies here. Put away those hats, tinfoil, 10-gallon, any hats really. Put your feet up and relax here with us at Slooh for a while. If you have any questions you'd like us to answer, or if you'd like to make any comments or observations, feel to tweet them at us. Use Twitter at Slooh, and you can join in with other viewers as well if you use our live chat room on slooh.com. If you're watching this show live on the website, you'll either find that chat room to the right of the show or beneath it, depending on your browser. But yes, we would absolutely love to hear from you. So a lot's going to happen today, and let's get started with that. So first, let's figure out what's going on in these live images. And to help us explain that, and to help us really understand that massive area of solar activity that brought us here, I'd like to welcome Slooh astronomer Bob Berman, a guy who has written a whole book on the sun called The Sun's Heartbeat, so he must know a thing or two about this ball of fire in our sky. Welcome to the show, Bob.
Thanks, Eric. Great to be here, and it's very exciting. Look at that great image.
I love that there's so much going on there, and let's try and unwrap that piece by piece. First, I'd love to establish sort of a baseline here. In terms of solar activity, that term's thrown around a lot, and I'm wondering if you could tell our viewers a little bit about what it means in terms of activity. Do we have a sun that occasionally goes to the gym sometimes, works out a bit, and then it rests for a while? I mean, then it's not as active. Like, what does activity mean when we're talking about the sun?
Well, we've known now for some time that the sun goes through cycles of more explosions on the sun, more emissions from the sun. It was only in the 1950s that Gene Parker revealed that there is a solar wind. He was ridiculed at first. A wind from the sun, well, it's not really air blowing, it's particles, broken bits of atoms streaming toward us at a couple hundred miles a second. And you figure about 10 particles for every bit of space the size of a sugar cube on average, but easily gets to 100 or more depending upon how active the sun is. So yeah, we've been observing this. And in an 11-year cycle, everyone's heard of the 11-year solar cycle, although this last one, cycle number 24, was 14 years long. The activity on the sun waxes and wanes, and it's very complex. It's very important. It affects us in lots of ways, and in some ways contradictorily or paradoxically. For example, when the sun is least active and you think, okay, we've got a break, we're getting less radiation hitting us, well, then the sun at that time does not act as a shield to stop the even more powerful intergalactic, well, I shouldn't say intergalactic, let's call it interstellar. It's from other places in our galaxy. Actually, some of the stuff may be from other galaxies as well. That stuff comes in and hits Earth. So the sun, when it's more active, acts as a shield and blocks some of the other stuff. So either way, we sort of can't win, but it does come in surges and cycles, and we're watching some of this live right now, today.
There's so much that's going on all the time, and thanks for just giving us that overview of that. And now what we're seeing is a very interesting sun that was captured by our partner Matt Francis at the Prescott Observatory just a little bit earlier last week. And there's just so much going on here in this image, this sun that we're seeing. Could you tell us a little bit about some of the features that we're seeing on this image that Matt captured, Bob?
Absolutely, Eric. First of all, understand the scale of it, that the sun is about 865,000 miles in diameter. That means about 108 Earths stacked side by side would go from one edge of the sun to the other. That's just in a line. In terms of volume, it would be over 1 million Earths would fit inside. So this is a big ball that we're looking at. And good. And there's the Earth to scale, just showing how we're dwarfed by the sun. But also, now let's look at the overview and look at the different features that we're seeing on it. And later on, we can talk about what's under the surface, because only in the last few decades have we learned that there's two separate suns inside the sun, balls within balls. But just what we can see on the surface, on the edges, look at those prominences. Those are like geysers of nuclear flame, magnetically channeled because they're broken bits of atoms. And you might remember from high school that the components of atoms, like electrons and protons, have an electrical charge, and things with an electrical charge are susceptible to being channeled by a magnetic field. So they follow magnetic field lines. That's what you're seeing along the edge. If one of those is right in the center, actually a little bit to the right of center, then it's positioned where the stuff that it blows out can come in our direction. All right, now we see white areas within the sun. Those are active sunspot regions, and the sunspots themselves are surrounded by bright areas called faculae. That's Latin for little candles. And then in addition to that, there are a few strings that we see, and those are essentially filaments, which are prominences like what we saw on the edge, but the prominences, when we're looking down on them, look like black strings. And now here is an hedgerow. This is a really wild one. It's not just a single prominence. It looks like a whole phalanx of them, almost like a line of thunderstorms, a squall line approaching us. And when this was on the edge of the sun, this is why, Eric, we were all so excited and a little bit nervous, knowing that if it's on the eastern edge of the sun, well, that's the edge coming right toward us. And in about 1 week's time, because the sun takes about a month to completely rotate, in 1 week's time, a feature on the edge will go from the edge to the center. Look at that white area almost at the center. It's just a little bit left or east of the center. That means tomorrow or the day after, it'll be dead center. And a couple of days after that, it'll be a little bit to the right or west of center. And when it's there, then the overall magnetic field lines of the sun will channel it in our direction, because stuff from the sun heads here like a giant spiral, like a lawn sprinkler. You know, that kind of spirally pattern that you see in water from a lawn sprinkler? Well, that's the path that the material will follow. So we have a few days of travel before that material gets into a position where it can sprinkle us with its violence. And during a big explosion, a CME, a coronal mass ejection, we can get up to 10 billion tons of material from the sun slamming into us. And that's when we really have to watch out.
So it's just, there's so much that's going on, and it's incredible to just get deeper and deeper into the sun. The more we dig, the more we tend to see. And even though the sun looks so crowded with activity right now, are there any things that can happen on the sun that we're actually not seeing happen on this current sun that we see in front of us here?
Yes, there's no coronal mass ejections right now. That's the most violent type of storm. It wasn't even discovered until the 1970s that such things could happen. Sure, we knew about flares, which are explosions on the sun. We knew about prominences, but the CMEs are the most violent of all. And if a really powerful one happens, for example, as happened in 1859 and again in 1921, or was it 1923? I think it was 1921. And then again in 1989, to a slightly lesser extent, then we get our satellites knocked out of commission. We get radiation in polar regions. For example, jetliners flying polar routes, all the crew and the passengers get more radiation than they would really like to get. And their radio communications are knocked out, so they can't communicate, which isn't a good thing there. And GPS gets knocked out. There have been cases of roads being paved, and when the GPS was knocked out, the roads were built in the wrong place and had to be torn up and redone. And these days, crops are planted according to GPS. So when those satellites are knocked out, the farmers have to just pull their tractors over and shut them off because they can no longer perform adequately. So our world has become so conditioned to satellites that depend on signals that can be knocked out by the sun.
Oh, Bob,
And
sorry to cut you off
things
here.
like fire starting. Yes.
Oh, no. We have a quick question from a viewer that we just wanted to push in here before the commercial break. But somebody was asking actually why these images are black and white as opposed to being in color. Isn't the sun in color? Is this what the sun actually looks like? Why are we seeing these
That's
black
a good
and white
question.
images?
The sun is actually white because it gives off all the colors of the rainbow. In fact, a rainbow is the sun's colors laid out side by side instead of combined. When you combine all the sun's emissions like a blender, put them into a blender, you get white. White is a rainbow in a blender, gives you white. So really a white image is what you get from the sun. Now, because the sun is too bright for us to image, it would ruin our equipment, it would ruin our eyes. We're using all sorts of filters, and then the result of that is we can bring you the image in any false color we want to, in green and red, in yellow. We could present it in yellow to make it look kind of the way people expect it to look, but in truth, it's filtered and cut down anyway. So the truest image would be something that's a white that's subdued. So that's what you're really seeing here. Yeah.
And so there's a lot of different ways to look at the sun. We're just seeing a few of those ways and a few of what the activities that the sun has to offer,
That's
so to
right.
speak.
And Eric,
But
since you have a degree in astrophysics, so you of all people know very well that we can also choose part of the sun's light in which to view it. In this case, we are viewing the sun only in the light of H alpha, hydrogen alpha at 65, 63 angstroms. And that precise wavelength of light is a very active, beautiful, busy, informative wavelength. Because the sun is giving off so much energy and so much wavelengths, it's easy to just choose one, and a very, very special and expensive type of filter that blocks out all the rest of the sun's emissions except less than 1 angstrom's worth of light coming only from the emissions that happen when the single electron of hydrogen tumbles down, is excited, and then tumbles down from the third possible orbit it could have down to the second possible orbit. And then it gives off a little bit of red light, which we could have shown in red if we wanted to, but that's what it is. It's a deep red light, 65, 63 angstroms, and we're viewing the sun right now. The Prescott live image that we're seeing of the sun at this moment is showing the sun in the emission of hydrogen light, and that brings out more detail, beautiful detail, that you wouldn't see if we were blurring it out by showing you all the emissions at once.
And yeah, I think that's a great point to bring up. The sun is sort of like a book, and each wavelength that we look at the sun in is a different page that tells us different information about it. But thank you so much, Bob, for joining me here for this segment. We're actually going to be right back with you in a moment to discuss the potential dangerous side effects of the solar flares and other solar activity in a moment, just after this short commercial break. But before that, though, to the thousands of people that are tuning in right now from all over the world, I wanted to take a moment to encourage you to join the expedition to explore the universe with us, which we do every day here at Slooh. Our members are not passengers, but rather sign on as working crews to take control of the robotic telescopes in the Canary Islands as well as Chile to share the most interesting places in space with everyone else in the community. Slooh is social exploration, and together we've already visited over 50,000 different places in the sky and captured 4 million photos. Working as a team makes it easy to learn from each other and share from our diverse perspectives, fueled in equal part by science and imagination, and the human spirit to search and wonder. We may be alone in the universe, who knows, but you'll never be alone at Slooh. I also wanted to share a little secret with you. A year in the making, there is a new Slooh coming. That's right, smarter and more powerful than ever, and very soon. We are so excited to show that to you when it's ready, so stay tuned for that. Well then, you are welcome aboard Slooh's expedition into outer space, which is free to try. Do join our adventure into the great unknown. Now, don't go anywhere. The sun may be clouded over, but we have just started, and maybe the sun's gonna appear right back again. We'll see. Unpredictability here. We'll be right back after this quick commercial break. Welcome back to Slooh, as we're looking at the sun as it's been throughout the week and live, interspersing those images and the evolution of the sun as we see it here. So Bob and I have been chatting about the sun for a while, and we're not quite done yet. Now, welcome back to the show, Bob. Thanks again for joining me for another segment here on Slooh. But we aren't really in any danger from this latest round of solar activity, but the Earth does experience the effects of solar flares and things all the time. And so I was wondering if you could give me, sort of in a generic sense, sort of grouping all the things that sort of come our way from the sun in general. We can go more into the specifics a little bit later, but what in general usually does solar activity cause when it approaches Earth?
Well, it probably started with Carrington in 1859 when he saw a section of the sun double in brightness. He could not know that this was the brightest solar flare ever observed. He was seeing visible light, but at the same time, X-rays were streaming from the sun, and it turns out almost all parts of the electromagnetic spectrum, that is, forms of light. Not too many radio waves. The sun is not very bright in radio waves, but certainly infrared. A little bit more than half of its energies come at us in infrared, which we feel as heat. Almost half is light. About 7% is ultraviolet. And as I said, we even get X-ray explosions heading in our direction. So those are the things that travel at the speed of light and arrive in only 8.5 minutes after we watch them live here at Slooh. Boom, we're hit with them less than 10 minutes later. At the same time, actual solid particles are blasted off from the sun. Normally they take 4 days to get here. These are broken bits of atoms, protons, electrons, charged particles, but in a very powerful storm such as we had in 1921, they can get here in only 2 days. And then they smash into Earth's magnetic field, our magnetosphere, and what happens next depends, and this is why we can't always say, hey, there's going to be an aurora tonight, because particles are on their way, which they are right now, by the way, from the sun. But you can't tell for sure until that swarm of material, like a buzzing swarm of bees, hits our spacecraft named ACE, about 1 million miles sunward of us. And when it reaches there, that spacecraft measures the polarization of those particles. In other words, the swarm has its own magnetic field, and it's a 50-50 shot as to which way the north and the south part of that field is oriented. If it's oriented the same way our Earth's field is, where we say the north magnetic field is up and the south is down. In truth, a lot of people don't know this. The south field is actually up and the north is down, but we call that south field the north because it's in the northern part of Earth. Okay, so I'm sorry I even brought that up. But the point is, if this swarm's field is aligned the same way Earth's field is, well, then our magnetosphere channels all that stuff harmlessly past Earth and nothing happens. But if that swarm has a polarization that's opposite ours, that's a 50-50 shot, then it transfers its energy. And all of a sudden, along those magnetic field lines, you get charged particles, and this generates electricity. And I'm talking about big league electricity that makes lightning bolts seem like a little expired battery by comparison. This super electricity ionizes the air, mostly about 100 or 120 miles up. If it's oxygen, nitrogen will often get a green color at 5,000, just over 5,000 angstroms, or a red at 6,400 angstroms. But our eyes are very insensitive to red light, deep red light. So we see the green, and that's what makes an aurora, a green aurora, very, very common for us to see. So that's the story, and we of course love to see the aurora, and that's the good news about it. That's when the sun has an explosion that makes pretty colors and makes us feel in awe of the sun and doesn't do us any harm. And that can happen, and does happen almost every night if you go to central Alaska.
Right, and there's a viewer that has actually a follow-up question related to the aurora, and they're asking, they asked in chat, why does the solar wind only appear as the aurora borealis when it skims our atmosphere, and the solar wind that hits us head-on toward the equator doesn't?
Well, if I'm understanding correctly, why is it in the north and not along the equator? 5577 angstroms, actually. That's the oxygen glow. That's just where the eye is most sensitive. The reason is that our magnetic field, of course, is oriented with the north and south poles at high latitudes. They're not coincident with the geographical or the physical poles of rotation. Rather, they were located in Canadian territory. Just went into intercoastal waters just in the last few years. But it's still located a little under 1,000 miles from the north, the physical North Pole. So that's the area that's going to be most susceptible, where those field lines head straight downward. At the equator, where they're sideways, where their magnetic field lines are sideways, it makes it less susceptible for us to have any aurora reaction from it. And also you get less radiation there. If you actually measure the amount of cosmic radiation that comes from the sun throughout the year, a mid-northern latitude place like Japan or the United States, you're talking about getting in the area of 40, 50, 60 millisieverts per year, but you can have double that if you live at high latitudes, such as in Alaska.
And it's really interesting to see all these things that the sun is capable of. And one thing I was wondering in terms of follow-up to that is, can the sun maybe still surprise us? Because we do have knowledge of things that are coming our way nowadays. But actually, I think it was during the Cold War in 1967, they had a ballistic missile early warning system that went offline because of solar activity. And they thought there might have been some dastardly plot by another nation to turn this off. So it almost brought us over to the cliff of nuclear war there because of something the sun did that we weren't able to notice that was what the sun was doing. Are we observing the sun in enough detail? Do we have enough people on the case, enough machines out there sensing what they need to sense to really have a grip on what's going to be coming to us before it gets there? Or is there any way for that sun to potentially hit us unexpectedly in some way.
We're getting better and better at it, of course. That event in 1964, it's true, that could have triggered a nuclear war. And then we had another one in 1989 that at first was thought due to Soviet jamming that our signals weren't getting through, and it was thought the Soviets were up to some no good with that, because that was still before the Soviet Union had collapsed. Actually, the Soviet Union was starting to collapse just later that year. But it turned out that too was a giant solar storm on March 13th of that year. So we have gotten surprised, but less and less so, thanks to a new armada of spacecraft that are dedicated to studying the sun. At one time, we had things like POSE and ACE and TRACE on it, instruments like that. Now we have SOURCE and STEREO and the SDO, the Solar Dynamics Observatory, and we have ways of monitoring even the backside of the sun. So as the sun is rotating, we can see the stuff that's about to rotate into view. Crazily enough, we only have two disks in our sky, the sun and the moon. Everything else are dots. Stars look like dots. Planets look like dots to the naked eye. Two disks, and they both appear exactly the same size, because the sun is 410 times larger than the moon, and it's 410 times farther from the moon. So they're both the same size. And here's my point, they both spin in the same period of time. They both take 1 month to spin. So we have starting with that basic stuff, and now we're filling in things that we're learning more and more and more. We have new fields of study like helioseismology, where we're watching pulsations on the sun. The sun keeps shaking like a giant subwoofer, and the way it shakes tells us what's under the surface, so that we've been able to find a second sun inside the sun. We've known since 1920 that it has a core, a nuclear place of fusion that takes up only about 1/300th the volume of the sun. A little tiny sphere, ball in the very center of the sun, which every second gives off the same energy as 96 billion 1 megaton hydrogen bombs. Every second, 96 billion H bombs going off in this little ball that's so small you could almost not see it if you could penetrate the sun, because it's only at the very center of the sun is this tiny ball. But now we know, this is a new discovery, that 70% out from the center of the sun, there's another ball where the sun spins as if it were a solid rubber ball, and it spins uniformly. Whereas the outer layer of the sun, the photosphere that we see, a very thin layer, only a couple hundred miles thick, which is why it looks so sharp, that outer layer spins chaotically. The center of it, as we look at this live image from Prescott Observatory, the center of it takes 28 days to spin, but the poles take about 10 days longer to make a rotation. A chaotic spin, so that layers are brushing against other layers, and there's a conveyor belt of material that's slurped outward, other stuff that's slurping back inward. It's fascinating. There's so much more than we could have ever imagined once we started knowing what the sun was about in 1920, when Arthur Eddington first told us about the nuclear process that converts hydrogen to helium and told us why the sun and the stars shine to begin with. We've gone so far in that, almost 1 century since then. Hey, did you see that bird fly by?
It was a bird. It was not a plane or Superman. It was a bird.
A giant hawk just flew past the face of the sun there in Prescott, Arizona. Anyone who thinks that we have these images canned and that they're not live images, wow, that was just an amazing thing. I wonder if this is being taped in some way and we could preserve that and show that again sometime. That was just so beautiful. It was a hawk flying in front of the sun. I'm not crazy. I'm telling you, I saw it.
We see how dynamic it is. We see nature. We see the sun meet nature. This is a mixture. This is live. This is here on Slooh. But my goodness, this has been quite a show. Thanks so much, Bob, for joining us here today. This is about doing it for us here on Slooh, but I just wanted to ask really quick if you had any final thoughts in relation to the sun that we see.
Oh, just that it's so exciting, and as we lead up to the first total solar eclipse in 38 years in the United States, the most exciting event in decades coming up, the sun is going to be more and more the focus of global attention. And so it's great that we're doing shows like this, and I think we're going to be doing them more often as we head toward that event 1 year from now.
Well, thank you again so much for joining us here today, Bob.
Thank you, Eric. My pleasure.
And thank you again to, of course, Matt Francis from the Prescott Observatory for giving us these live feeds that were really, really particularly live today. It's just amazing to see sort of our perspective here on Earth and what we see with the clouds and nature interact with this, or interact with the image that we see from this thing far, far away from us in the depths of outer space. But before we go here today, I did want to let you know about a couple shows that were coming up here on Slooh at the start of September. We'll be looking at the sun once again. Bob mentioned that we have an eclipse coming up a year from now, but we also have the annular solar eclipse just coming up in September that's going to be passing over the African continent. So tune in for that. We'll be going live from Slooh with that, with a string of feed partners that will travel or show us the path of this eclipse as it continues across our planet. And so that's going to be on September 1st. And then following that day, we're going to be looking live at the new moon as it begins to peek out from the sun. So during that show, we'll be diving deeper into the importance of the new moon to the Islamic faith. So we're going all around the world exploring all that astronomy has to offer and all how we relate to it on this planet Earth here. But thank you again to all you viewers out there for joining us here today. We're going to be jam-packed with a lot more content coming up soon, so we hope to see you again. And have a great rest of your day. This has been Eric Edelman, and you've been watching Slooh.com.